All right, well, welcome back, folks. Hopefully, you had a chance to watch the video yesterday afternoon. I know that I'm asking a lot of you to be able to watch videos and try to get the material comprehended and try to get the material, wrap your mind around the material. But I think this moving forward, this way that we're going to be carrying out our classes will work for us. Um, because I think having that break in between the two lectures will help you. Again, try to watch it if you can, folks. The second lecture, the afternoon lecture, is informative. It's more for your information and to get caught up with the material. It's only this morning lecture where I'll ask you to turn in some work. Okay? And so we left off yesterday afternoon with the discussion of how photoelectron spectroscopy works. Okay? So photoelectron spectroscopy, like I mentioned in the afternoon lecture, is that it's a method by which we can visualize and take a look at how electrons situate themselves around a nucleus. And so this is one of the few pieces of evidence that we have that is not mathematical that allows us to locate the electrons. Okay? Now, again, what we're doing is we're locating electrons based upon their energies. We can use those energies then to calculate them for the orbitals that they are in, and so therefore locate them around the nucleus. Okay? And so what I wanted to do is what we started talking about yesterday afternoon is I was talking about how photoelectron, how these machines actually work to separate out these electrons. Because if we can't effectively separate out these electrons and differentiate them, then the information we obtain is not very useful to us. And so the unique and the way that these instruments, these machines, are able to separate out the electrons is really unique. And so so I wanted to go over it with you, and we started going over it yesterday afternoon, because I think everything you've learned up to this point in terms of the energies of the electrons, in terms of how kinetic energy is related to the motion of these particles, and how we can use that kinetic energy and calculate then for the energies of the electrons themselves and where they were situated at in terms of their ionization energies. All that we learned earlier, and we're going to use that to understand then how this machine here is able to separate out electrons so that we have different types of electrons that we can use to figure out the structure of the atom based upon those electrons. Okay? All right, so with that said, let's go ahead and let's continue on here with where we left off with yesterday. And just let me review this for you. So what we have here basically, and so do you need to understand, will the AP exam ask you about this? Absolutely not, they won't. But if you have an understanding of how these electrons, how we obtain these photoelectron spectrographs, okay? If you're able to understand that, you'll understand what information is given to you on the spectrum itself, and having that understanding will make things really easy for you. Okay. All right. So with that said, then what we're doing is we're looking at the inside of the machine that we saw on the previous slide. Okay. And so we have our sample here. So what we have to do is we have to vaporize the sample here. So we have the sample in here, okay? And then we inject the sample in at this port right here. Okay? And so the sample is sitting here waiting for us. What happens then is we need a source of high energy photons. The reason why we need a source of high energy photons is what we're doing is we are going to collide those photons up against the sample atom. Okay? And in the course of that collision, what you're basically going to do is you're going to blow up the electrons. You're going to push the electrons out. So what's going to happen is the high energy photons come in, they collide against the atoms of our sample, and they push the electrons out. The process here is very similar to what we saw with the photoelectric effect when we talked about that. Remember the photoelectric effect? We took light and high energy photon light, and we hit it, a piece of metal with that light, and depending on the frequency of that light, and remember the frequencies that related to the energy, as we saw here using Planck's constant here. If we hit it with a certain frequency of light with a certain amount of energy, then what happens is that those electrons get emitted, we detect it, currents detected, and that was the photoelectric effect. The idea behind photoelectron spectroscopy relies upon that photoelectric effect in that what we're doing is the same thing. We're going to be hitting the sample now, not as a metal, but as a gas, as a vaporized sample here. We're going to hit it with some high energy photons here. Typically in the past, they've used X-rays and UV light here as well. What they do now is they use helium. So we have a helium source in here, and we hit it because helium is a fairly large atom. However, relative to photons. However, when you energize the helium, they emit very high energy photons here on the scale of with the energy of roughly about 21 electron volts. And that's enough energy. That's enough energy to pretty much cause the emission of electrons from most atoms and from most molecules as well. Okay, so the collision occurs in here, and once the collision occurs, what happens is that electrons will be emitted. The electrons will be emitted, and they will enter into this chamber here. They will enter into this chamber here, and in this chamber here, what we're going to do is we're going to generate an electrical field. So we will have an electrical field that we will generate electrical field. We're going to generate an electrical field, okay, inside this chamber here. And the reason why this works, folks, is because remember, electrons are negatively charged. Okay, so electrons are negatively charged. They're going to go into this electrical field here, and they're going to be repelled by the negative side here and attracted to the positive side. And so they will follow this pathway here. Okay, so there is a little chamber here, okay, a little pathway that they can follow. Okay? And so the electrons move in. They will be repelled by the negative side, attracted to the positive side, and depending on how fast these electrons move, okay, that is how, so depending on their speed, they will either bend and head towards the detector, or they will fly outward, okay? So the electrical field here is used to force certain electrons along this pathway. If these electrons move too quickly, they will not follow this pathway. If they move too slowly, they will bend prior to get to the end. So what happens is we can set the electrical field. We can adjust the electrical field here. We can adjust this electrical field in order to allow only certain types of electrons with the right speed here, okay, to move through this this pathway here and end up at our detector. Okay, and so depending on how we adjust this electrical field, certain electrons will bend and get towards the detector, and others will not. And so by changing the electrical field will allow certain other types of electrons in as well. Okay, so the speed here corresponds to kinetic energy. Okay, because remember, we can calculate for the kinetic energy, because if we know the mass of electron, which we do, and we can determine its speed, we can obtain the kinetic energy. But more importantly, there's a relationship between speed and kinetic energy. That means then, if we adjust the electrical field here, at a certain adjustment level here, what happens is only certain amounts of, only the specific type of electron with the specific type of kinetic energy can bend towards that detector. Okay? And so what we want to be able to do is we want to be able to determine then which atoms and differentiate the atoms in terms of their kinetic energy. Okay? And there is an important reason why we need to do that. So by the time the electrons get here, the only electrons, based on the adjustment on the electrical field here, the electrons that end up here will all have a particular kinetic energy. That they will all have a certain kinetic energy that we can use then to relate back to the ionization energy that held them in place in the first place. Okay, so what we're going to do then is in the next slide then, we're going to examine then this relationship, the relationship then between kinetic energy and ionization energy. And we want to be able to do that because it's this here that we want. We want the ionization energy because based on that, we can determine then where the electron's located. Is it located closer to the nucleus or is it located further away from the nucleus? Okay? And so that is why an understanding of this particular, how the photoelectron, how this machine works, allows us then to understand what we're looking at when we look at the spectrum itself. Okay. All right, very good. So let's go ahead and let's take a look at the, let's blow up and take a look at what's happening within this chamber here, okay? All right, so this is what we have. Here is, so let's go ahead and take a look at what we have here. So here's our high energy photon. Here is a photon of energy right here. Okay, so this is our photon. Okay, this is our photon of energy. Okay, and remember this is going to be from helium, for example. So that photon of energy comes in. That photon of energy, remember, that energy we can calculate for, and it's given to you here using Planck's constant and the frequency of the wavelength of the photon itself. So here it is, the photon comes in, okay? And remember then the wavelength here, we can calculate for the wavelength here. This wavelength here is if we know the speed of light, okay, and the frequency here, okay? So if we know this wavelength, we can calculate for the frequency, plug it in right here, get the energy, okay? So that was back in chapter 6, so make sure you review that. So we can calculate for that energy. We know what this energy is of the photon. So this is the E of the energy of the photon. It's going to come in. Here's our sample right here. Here's our sample. Let's go ahead and write that down. Here's our sample atom. Okay, so the photon comes in and it hits our sample here, and the electrons are out here. Okay, so this energy here, this energy represents the ionization energy. Okay, this is the ionization energy. This is the energy that holds the electrons in place. And if this photon is at the correct frequency, it has the right energy, it's going to push the electrons out. Okay? And it's going to push the electrons out. And so as they push it out, again, like we said here, certain electrons are going to move here. And this electrons then, so these electrons will have a higher speed. These are the lower speed electrons. The higher speed electrons will take a broader path. Okay, the lower speed electrons will take a smaller path, a shorter path. The way that you want to kind of imagine this is that if a car is moving at a very high rate, it has to take a longer curve. It has to angle out further in order to make the turn. If it's moving slower, it can take a sharper turn. And so electrons that are moving at a higher rate has to take a longer pathway in order to get around this curve here. And the electrons with that are slower will take a sharper turn around this pathway here. Again, we don't want the fast electrons. Okay, so these are electrons that are moving at a very high rate. These are the electrons that are moving at a very slow rate. We want the electrons that move just in the middle right here so that they can end up at the detector on this side. Okay, so the detector here. So these are the electrons here with just the right amount of kinetic energy. So this represents the kinetic energy of electrons here, and they will have just the right amount of kinetic energy to make that turn. They won't turn too sharply. Remember that we have the electrical field set up here with the negative and a positive and negative end there. Okay. And so if they're moving too slow, they're going to bend in too sharply. If they move too fast, they're going to move too far out. We want the electrons that, based on our adjustment here, we want the electrons that will move at just the right speed to get them around that turn and into the detector over here. Okay? So there are the electrons with just the right amount of kinetic energy. Okay? And so at this point, then we can get the kinetic energy if we know then we can calculate the speed, get those electrons around. Okay? All right, so with that said, then, if we go back up here, you're going to see then the ionization energy here. So this is going to be our ionization energy. Make sure you keep this in mind. This represents the energy of the ionization energy, and this represents the kinetic energy here. The total amount of energy of the ionization energy, which we remember refers to the energy needed to remove an electron from the nucleus, okay, from the atom, and the kinetic energy here, that has to be equal to the energy that you started out with, okay, which is the energy of the photon. Okay, so this is the energy of the photon. Okay, that has to be equal to the ionization energy. And so remember, what we want to be able to do is we want to be able to get that ionization energy. We want to know where the electron is located because the location of the electron will determine its ionization energy. The closer the electron is to the nucleus, the greater the ionization energy. The further electrons away from the nucleus, the higher, the lower the ionization energy. And so let's make sure you understand what's going on here. And so let's finish up here. Let me erase this really quickly. Okay. What we're taking advantage of then is the kinetic energy here and its relationship to the ionization energy, because this will be constant for the most part as you shine in the light. Okay, this will be constant for the most part, okay, and we're just adjusting the electrical field here. So you can imagine then that if you have a higher kinetic energy, that means then the electrons that we are capturing here has a higher kinetic energy. Okay? That means then they will have a greater speed. They are moving at a greater speed. Okay. All right. And so with that said, then if the kinetic energy is greater, okay, so if the kinetic energy is greater, they're moving at a higher speed. You can imagine then that the ionization energy is low. Okay. Low ionization energy means that the electrons are not held as tightly. Low ionization energy means that the electrons are not held as tightly, and so therefore you will have a greater kinetic energy. Okay. And so this is the relationship that you have to take advantage of here, and that is you have an inverse relationship between kinetic energy and ionization energy. As ionization energy increases, the kinetic energy is going to decrease, okay? And therefore you have a slower moving particle. You have a slower moving particle, which means then that it's going to take more. It's going to take more of this energy of the photon to remove the electron. And if that's the case, then when the electron leaves, it's going to have less kinetic energy, meaning that it's going to move slower. And so you have to adjust the electrical field here to get it through. Okay. All right. So, and so that's how we can get this ionization energy. Okay. That's how we can determine this ionization energy here. And so keep that in mind. Keep that in mind. That's going to be useful for you. And so let me go ahead and write this down for you. Okay. And so in the end, then what we want to do then is we want to make sure we understand that there is a relationship that we can take advantage of here. And that is there is an inverse relationship between kinetic energy and ionization energy. Okay. As the ionization energy increases, we're going to have a smaller and less kinetic energy. Okay. And if there's less kinetic energy, again, the particle is going to move slower. Okay, and so make sure you keep this in mind. That kinetic energy is directly proportional to velocity. And remember, this is the square of the velocity, but let's just keep this simple here. Okay, so as the velocity increases, kinetic energy increases. As velocity decreases, the kinetic energy decreases. So this is what we can take advantage of in order to understand the photoelectron spectroscopy. Because when we look at the spectrums in just a moment, we are actually looking at the ionization energy as compared to the number of electrons that have that particular ionization energy. And this is how we determine the ionization energy of these photons themselves. Okay, all right. And so hopefully you were able to get that. Hopefully you're able to get that from the POGIL activity that we did that I asked you to do yesterday. So we'll be going over that in just a moment. Okay. All right. So let me go ahead and clear this out. Let's continue on. Okay. And let's take a look at this was taken from your POGIL activity. And so what I would like you to do is, if you don't have your POGIL activity, go ahead and get that real quick. What I'd like you to do is show me your work. So hopefully you have this done already. So on your paper here, I'm going to give you a couple minutes, about a minute or so, to write down your work here, and then we'll compare answers, and I'll work it out for you. But take about a minute. Okay, write down what you got on your from your POGIL activity. Okay, so this is from POGIL activity for the photoelectron spectroscopy. Okay, and show me how you did this calculation. Okay. And then we'll go over it when you get back and unpause the video. Okay? All right, go ahead and do so, and make sure you type in your answer into the Edpuzzle activity, Edpuzzle lecture as well. Okay. All right, so go ahead and get that done. All right, let's go ahead and let's take a look at what we have here. Okay. So what we're asked to do in this particular problem, is that they want us to find and calculate the ionization energy for the electron here. Okay. And so the photon of energy that, so we're going to hit the atom with this particular photon of energy here. So the photon has this amount of energy, okay? And then when the electron leaves, it has this kinetic energy, okay? And so you can imagine what's happening here, folks. What's happening here, and let's go ahead and visualize this. So here's our atom. Let's go ahead and just, let's call this the generic atom here. And this is our electron that's sitting out here, okay? So we're looking at this electron here. So our photon of energy here is going to move in. Okay? So our photon of energy here, the energy of the photon is 143.4 megajoules per mole, which is equivalent to the electron volt that I talked about here. Okay, okay. And remember, the electron here is held in to this nucleus here by an ionization energy. Okay, so a certain amount of energy is holding this electron in. We talked about this. We can calculate for that using Coulomb's law if we needed to. Okay, and so the electron is being held in by this particular energy here. So remember, there are three energies that we're looking at when we look at photoelectron spectroscopy. The energy of the photon, so that's it here. So here's our photon. Let's imagine that this is our photon here, okay, of mass m. The photon comes in with this energy here. Okay, the ionization energy holds in the electron here, and then if this photon of energy here, if the photon here is energetic enough, it's going to push out that electron. Okay, and so when that electron leaves, it's going to leave with that amount of kinetic energy, which we are told then is 114.8 megajoules per mole. And that's the idea behind the photoelectric effect. And so can we calculate for this ionization energy here? Well, of course we can, because remember the energy of the photon, the total energy has to be equal to the energy of the ionization energy, plus the kinetic energy. And that's it, folks. And so if you keep that in mind, then we can go ahead and define the ionization energy. We're going to take the kinetic energy and we subtract that from the energy of the photon. So the energy of the photon minus the kinetic energy, and that will give us our ionization energy. So the energy of the photon then is 143.4 megajoules per mole minus the kinetic energy, which is 114.8 megajoules per mole. Okay, and so with that said, then the ionization energy of this particular electron is going to be 28.6 megajoules per mole. Why we need to know this is that when this electron leaves, okay, we know then that wherever it was located at, it was located at a position where it took this much energy to hold it in place. We can then go ahead and let's say compare it to an electron that is further out. And so let's go ahead and consider this here. Okay. If we consider an electron that is a little bit further out, okay, the ionization energy here, and let's consider this here, the ionization energy here for this electron should be less. So this electron's further out, so the ionization energy for this particular electron should be less. And so therefore then, the kinetic energy here that this electron has, as opposed to this one, this electron here, when it leaves, it's going to leave with the higher kinetic energy, which means that its ionization energy here is going to be smaller. So if you do that math there, you're going to see that. So that's how we can do that. We can use this particular calculation then to differentiate and to determine then the location of an electron. Okay, so make sure you understand then, since this electron here, the one that we're looking at here, which left with 114.8 megajoules per mole of kinetic energy, that's going to be further in than this electron here. Okay? And as it leaves, okay, if the kinetic energy is going to be greater for it, and again, make sure you understand why. The reason why the kinetic energy for this electron here, when it leaves, when it gets bombarded by this photon here, when it leaves, okay, and we'll call this electron number 1 and this electron number 2. When this electron leaves then, it's going to leave with a greater kinetic energy. It's going to leave with a greater kinetic energy because its ionization energy was smaller. It's further away. It's not held in as tightly. So when that electron gets hit by this photon of energy here, its kinetic energy is going to be greater. It will have greater kinetic energy. You'll be moving at a higher speed. So therefore, its ionization energy will be lower. It's this here. It's this value here, which we can use then to determine then the location of the electron itself. Okay, and so that's what we'll pick up with this afternoon, and then we'll examine a few spectrum. We'll take a look at a few spectra here and understand what that means. But when you look at the spectrum, when you look at the spectra of a photoelectron spectra, what you typically have here is the ionization energy, the energy. Yeah, let me go ahead and do this real quick. And just a preview here. They're going to, you'll see then energy along the x-axis here, and effectively number of electrons along the y-axis here. And it's this energy here that is highlighted for us here, and that's where we get this energy from. Okay? All right, so that's why you need to know this. Okay, and so electrons with higher energy will be located, or the difference in energy will result from a separation of these electrons themselves. And so that's why we had to go over this, and that's why we need this background here to understand then where that we get that information from. Okay. Now the relative number of protons we'll talk about later. You don't need to know how we determine that. That's more of a when it gets to the detector was able to sort that out for us. Okay. But this is what you need to know, and that's why we did this calculation here. Okay. And that's why we went over it this morning. Okay, so this afternoon then, for the afternoon lecture, we're going to talk about then how we can translate this material into graph form and be able to read then the photoelectron spectrograph. Okay? All right, folks, so very good. Have a good the rest of your morning, and then I will see you this afternoon. Okay.